All right, we're in the Pilot's Handbook of Aeronautical Knowledge. This is chapter 4-7, 4-7 lift, right after weight. The pilot can control the lift anytime the control yoke or stick is moved fore or aft. The angle of attack is changed. As angle of attack increases, lift increases, all other factors being equal. When the aircraft reaches the maximum angle of attack, lift begins to diminish rapidly. This is the stalling angle of attack, known as the coefficient of lift max critical angle of attack. Examine 4-9, noting how the coefficient of lift increases until the critical angle of attack is reached, then decreases rapidly with any further angle of attack, any further increase in the angle of attack. Before proceeding further with the topic of lift and how it can be controlled, velocity must be interjected. The shape of the wing or rotor cannot be effective unless it continually keeps attacking new air. If an aircraft is to keep flying, the lift-producing airfoil must keep moving. In a helicopter or gyroplane, that is accomplished by the rotation of the rotor blades. For other types of aircraft, such as an airplane, weight shift controls, or gliders, air must be moving across the lifting surface. This is accomplished by the forward speed of the aircraft. Lift is proportional to the square of the aircraft's velocity. For example, the airplane traveling at 200 knots has 4 times the lift as an airplane traveling at 100 knots, if the angle of attack and other factors remain constant. We do 100 knots squared, 100. Actually, an aircraft could not continue to travel in level flight at a constant altitude and maintain the same angle of attack if the velocity is increased. The lift would increase and the aircraft would climb as a result of an increased lift force. Therefore, to maintain lift and weight forces in balance and to keep the aircraft straight and level, not accelerating upward in a state of equilibrium, as velocity is increased, lift must be decreased. This is normally accomplished by reducing the angle of attack by lowering the nose. Conversely, as the aircraft is slowed, the decreasing velocity requires increasing the angle of attack to maintain lift sufficient to maintain flight. There is, of course, a limit to how far the angle of attack can be increased if a stall is to be avoided. All other factors being constant, for every angle of attack there is a corresponding airspeed required to maintain altitude in steady unaccelerated flight. True only if maintaining level flight. Since an airfoil always stalls at the same angle of attack, if increasing weight, lift must also be increased. The only method of increasing lift is by increasing velocity if the angle of attack is held constant, just short of the critical or stalling angle of attack. Lift and drag also vary directly with the density of the air. Density is affected by several factors: pressure, temperature, and humidity. At an altitude of 18,000 feet, the density of the air has 1/2 the density of air at sea level. In order to maintain its lift at the higher altitude, an aircraft must fly at a greater true speed for any given angle of attack. Warm air is less dense than cool air, and moist air is less dense than dry air. Warm air is less dense than cool air, and moist air is less dense than dry air. Thus, on a hot, humid day, an aircraft must be flown at a greater true speed for any given angle of attack than on a cool, dry day. If the density factor is decreased, then the total lift must equal the total weight to remain in flight. It follows that one of the other factors must be increased. The factor usually increased is the airspeed or the angle of attack, because these are controlled directly by the pilot. Lift varies directly with the wing area, provided there is no change in the wing's platform. If the wings have the same proportion in airfoil sections, a wing with a platform area of 200 square feet lifts twice as much as the same angle of attack as a wing with an area of 100 square feet. Two major aerodynamic factors from the pilot's viewpoint are lift and velocity, because they can be controlled readily and accurately. Of course, the pilot can also control density by adjusting the altitude and control wing area if the aircraft happens to have flaps of the type that enlarge the wing area. However, for most situations, the pilot controls lift and velocity to maneuver an aircraft. For instance, in straight and level flight, cruising along at a constant altitude is maintained by adjusting lift to match the aircraft's velocity or cruise speed, while maintaining a state of equilibrium in which lift equals weight. In an approach to landing, when the pilot wishes to land as slowly as practical, it is necessary to increase lift to near maximum to maintain lift equal to the weight of the aircraft. We'll hold off right there. That was on 4.7. That was lift in chapter 4. Yep. See ya.